This program is about Unit 13 of the complex analysis course, and mainly it's going to be about bilinear transformations. Bilinear transformation is a transformation of the form z goes to az plus b over cz plus d, where a, b, c and d are complex numbers such that ad minus bc is not equal to 0. Why are we interested in bilinear transformations? Well, in Unit 13, we take a slightly different point of view of complex functions than we've taken in the rest of the course. Up to now, we've concentrated on their analytic properties. But in Unit 13, we look at them from a more geometric point of view. That is to say, we think of complex functions as defining transformations of the plane to itself. And the point about bilinear transformations is that they contain, as particular cases, some transformations which are very important in elementary geometry. I'm thinking of, for example, the transformation of translation, which you slide the plane parallel to itself rigidly, rotation, which you rotate the plane rigidly about a fixed point, magnification and contraction of the plane towards an origin. But there's one other transformation, bilinear transformation, which is of geometric importance, and that's the transformation z goes to 1 over z. We call that transformation inversion. Actually, to be perfectly honest with you, it's the transformation z goes to 1 over z bar, which is of greater importance in geometry, but the relationship between the two is not very hard. It's just got by complex conjugation. And complex conjugation just corresponds to reflection in the real axis. Now, inversion is just a little bit more difficult to picture than those other transformations that I mentioned. And I've got here a machine which will help me to show you how it works. This machine shows you geometric inversion. Z goes to 1 over z bar. It works like this. It consists of a number of rods which are loosely jointed together, so I can move them about like this. You see? Now this point here is fixed to the baseboard. Now, to generate the transformation of inversion, I do the following. If I want to find the image of a point, say here, I move the machine such that this marker coincides with that point, and this other point over here is then the image. So, for example, if I want to find the inverse of this point here, then I move the marker till it coincides, and this point is the image. Well, I should be able to use that machine a little later in the program to show you some of the geometric properties of bilinear transformations. But before I do that, there are one or two things that I ought to point out to you. Suppose we take a bilinear transformation, so it goes to az plus b over cz plus d, then if c, this number here, is non-zero, then that transformation is defined everywhere in the complex plane except at the point minus d over c. Of course, if c happens to be 0, then it's defined everywhere. And in fact, this transformation has a singularity, a simple pole, at the point minus d over c. It turns out to be a one-to-one transformation, and its inverse is defined again on a punctured plane, a plane with a point removed. This time it's the point a over c that's removed, as c is not equal to 0. One other point, it's an analytic function on the region which it's defined, and it's very easy to calculate its derivative, and the derivative turns out to be non-zero, nowhere 0. Now, as I said, I'm more interested really in the geometrical properties of bilinear transformations, and there are two of considerable importance. The first is this. The bilinear transformation is what is known as conformal. Now, that's a word I'm going to use a couple of times during this program, so I better make it clear what it means. If you have a point, and say you have a pair of curves which both pass through that point, then you apply a bilinear transformation to that situation as the image of the point. Those are the images of the curves. And the property of being conformal amounts to this. If you look at that angle, the angle at which the curves meet is the same as the angle at which the original curves meet. I'm afraid the drawing isn't too good, but I hope you see what I mean. And the bilinear transformation is conformal simply as a result of the fact that it's derivative is not 0. Now, a bit more specifically about bilinear transformations, they have the property that if you take a circle or a straight line and apply a bilinear transformation, then you get a circle or a straight line. Now, that's quite easy to see if you were thinking about rotations and translations, for example. A lot less easy to see if you're talking about inversion. And that's what I want to use the model for, to show you, to demonstrate to you that that is in fact the case. Now, you may have noticed earlier that I've got an extra rod here. And the idea of this extra rod is that it's got some holes drilled in it, and there are some pegs in the baseboard. So I can slip that hole over the peg, and now this point, of course, is constrained to move on a circle. And here I've got a pen so that you can see on this piece of card the image of the circle. So I make this point describe a circle. And there, the image of that circle was a circle. And in fact, that will always be the case unless the circle that you're mapping passes through the singularity of the bilinear transformation. And in this case, the singularity of the bilinear transformation is just here. It's at the fixed point. So, to show you what happens to a circle which passes through the singularity, I use another peg and another hole, and this time we arrange matter so that distance is equal to that distance. This thing now describes a circle which passes through the singularity. Put the pen back in again, and now watch what happens. See, it draws a straight line. And in fact, you can think of this as a rather complicated pair of compasses, if you like, for drawing straight lines. So that's the situation. If you have a bilinear transformation, in all likelihood it has a singularity. And then if you look at the image of a circle or a straight line, it'll be a circle, unless the curve that you started off with happened to pass through the singularity, in which case it'll be a straight line. Now, I think you'll agree that's all a bit confusing. It's a bit confusing to have to deal with these special cases. It would be jolly nice, wouldn't it, if we could somehow eliminate the special cases. Well, that we can do, and the following device is the way we do it. If we consider the bilinear transformation, az plus b over cz plus d, for which c is not equal to 0, and look at the limit as z goes to minus d over c of az plus b over cz plus d, then that's infinity. And the limit as z goes to infinity of az plus b over cz plus d is a over c. And a over c, you remember, is the point that you have to leave out of the domain of the inverse transformation. So what this suggests is the following, that we add to the complex plane an extra point, somehow, called the point at infinity, but we can consider our bilinear transformation as defined on this extended plane with the extra point, in such a way that the point minus d over c is mapped to the point at infinity, the point at infinity is mapped to the point a over c. And now let's think what happens to a circle or straight line through the point minus d over c, the singularity. It's going to get mapped to a curve which passes through the point at infinity. And what can be more natural than to think of the straight line as just being a circle which passes through the point at infinity? So that's quite satisfactory, really. And the only difficulty that remains is to try and picture, in some way, how this point at infinity has been added to the complex plane. Well, let's just think about that for a second. Here's the plane, and the point at infinity somehow has to be very far away in all directions. It has to lie on every straight line. Now, if you've got the right kind of sort of peculiar imagination, then you might think of the following thing happening. Suppose we bend up the complex plane until it sort of meets at an extra point, the point at infinity, somewhere overhead. Now, that may sound a bit ridiculous, but in fact, that's exactly what we do. And I'd like to show you that now. Here we've got a model of a sphere. We'll call this point the North Pole, and then this is, of course, the South Pole. And what we have here is a plane, which is the tangent plane to the sphere at its South Pole. And you're to identify this plane this tangent plane, as the complex plane, and the south pole as the origin in the complex plane. Now what I want to do is to show you how to make the points of the plane correspond to points of the sphere in a certain way. Well, I'll just switch on the lights. And now you can see a point in the plane and the corresponding point on the sphere. Now this model is transparent at the back, and I can turn it round to show you how that correspondence between those 2 points has been made. You see there's a line of light joining the North Pole to the point on the sphere. And that line carries on through the point on the sphere to meet the plane at that point on the plane. So that's how the correspondence is made. It's made by drawing a line to the North Pole, and it joins the 2 points which correspond. And we call that correspondence stereographic projection. Well, I'll just switch off. We're going to talk a bit more about stereographic projection now. And one thing that I must point out to you is that every point on the plane gives me a point on the sphere by stereographic projection. But if I take the North Pole of the sphere, it doesn't correspond to any point on the plane. Every other point on the sphere corresponds to a point on the plane, but not the North Pole. Let's think of let's say a sequence of points in the plane moving out towards infinity, and think about their stereographic images. There'll be a sequence of points moving up towards the North Pole. And if I think of a little neighborhood of the North Pole, it's the stereographic image of a region a long way away from the origin in the plane. And so what that suggests, of course, is that we take the North Pole to be the point at infinity. So that's the idea. Here is our model of the extended complex plane. It consists of the sphere, together with the North Pole, which is in the role of the point at infinity. Now then, the sphere and the plane are related by stereographic projection. Obviously, it would be nice to know if there are any sort of geometric properties which are preserved by stereographic projection. We can easily see that distance relationships aren't, in fact, preserved by stereographic projection. For example, if I take a pair of points close to the North Pole on the sphere, then their images will be a long way apart in the plane. If I take a pair of points the same distance apart near the South Pole, their images in the plane will be close together. However, stereographic projection is a conformal map, and I'd like to show you how that works on the next model. Here's the plane and the sphere again, and drawn on the plane a pair of lines. And you're to think of those as the tangents to a pair of curves which meet at this point here. Here, drawn on the sphere, are the stereographic images of those lines. And they're generated as follows. I have to join all the points on this line to the North Pole and see where they meet the sphere. Well, the points on that line, together with the North Pole, generate a plane which runs somewhere like down there, if you can see, which cuts the sphere in a circle, of which we've drawn just an arc. So you see a straight line corresponds to a circle passing through the point of infinity. Here's the arc of the circle which corresponds to that point. And now what I want to do is to convince you that this angle is the same as that angle. Well, actually, I'm going to look at this angle first. If I think of the tangent plane to the sphere through the North Pole, it's parallel to the plane we started off with. And the tangents to these two circular arcs are parallel to the two lines we started off with. So that means that this angle is equal to this angle, the angle at the North Pole. Now then, if I look at this sort of piece of orange that I've got on the surface of the sphere, it's symmetrical about a plane through the center of the sphere and equidistant between those 2 points. And since it's symmetrical, that means that this angle here is just the same as this angle here, and that, of course, is the same as the angle that we started off with. So the mapping is conformal. Now, it's quite interesting to investigate the geometry of the sphere a bit from this point of view, in particular to look at transformations of the sphere to itself. And that I'm going to do at the next model. The kind of transformation of the sphere to itself that's most interesting is a rotation. If I make a rotation of the sphere, then, and I map corresponding points to the plane by stereographic projection, then I generate a transformation of the plane. Rotation is a conformal map of the sphere. It preserves angles. Stereographic projection is a conformal map. It preserves angles. And therefore, the corresponding transformation of the plane also preserves angles. And it turns out that it has to be a bilinear transformation. If you have a rotation of the sphere, it generates a bilinear transformation of the plane. What I want to do with this model is to look at one particularly simple kind of rotation, rotation through 180 degrees about an axis lying in the equatorial plane. The ends of the axis are shown by my fingers there. 180 degrees about that axis. And we want to try and see what's the bilinear transformation which corresponds to that. And the idea is to look at what the rotation does to some of these curves which are marked on the sphere, and see what the corresponding transformation of the plane must do to their images. So, for example, if I take the equator, and this rotation maps the equator to itself, the corresponding curve in the plane is a circle whose center is at the South Pole, at the origin, and in fact it's the unit circle. So the unit circle is mapped to itself, not point by point, I mean the points aren't kept fixed, but in particular the ends of the points that correspond to the ends of the axis of rotation are left fixed. Here's this dotted line is the circle parallel to the equator. Here's its image. It's the stereographic image of this circle here. If I carry out the rotation, see what happens. Let me get the thing back on again. There we are. It's now moved below the equator and corresponds to this circle. And in fact, the outside of the unit circle, which corresponds to the northern hemisphere, gets mapped to the inside of the unit circle, which corresponds to the southern hemisphere, and vice versa. The North Pole, the point of infinity, gets mapped to the South Pole, which is the origin, and vice versa. And finally, if we look at this line of longitude, which corresponds to a straight line in the plane, which we may as well take to be the real axis, that's mapped to itself by the rotation, and so the real axis is left fixed. So we're going to look for a bilinear transformation which has all these properties. Maps the point at infinity to the origin and vice versa. Leaves the unit circle fixed. And the bilinear transformation that does that is z goes to 1 over z. It's inversion again. So here we have another way of looking at inversion. Well, it's quite interesting to pursue this idea and look at other rotations. They're a little bit more complicated to deal with. And we're going to finish up the program by showing you some pictures of the bilinear transformation that corresponds to a rotation of the sphere about an axis which isn't horizontal, a rotation like this. This is the sphere. We're looking down on it from above. And in the upper right-hand part of the picture, we're going to show you the complex plane. This is the axis about which we're going to do the rotation, and these are the corresponding points in the plane. Next, we're going to show you some curves on the sphere and the corresponding curves in the plane. These are circles on the sphere which are circles of latitude based on the axis of rotation. And the corresponding curves in the plane are circles, and they make this pattern rather like magnetic lines of force based on the 2 points corresponding to the ends of the axis of rotation. And now we look at the lines of longitude. And the corresponding curves in the plane are circles which pass through the 2 points which are the ends of the axis of rotation. That line is the particular case of the circle and the sphere that we're looking directly down onto. Now we're going to do the rotation. As we do it, then a line of latitude is, of course, left fixed by the rotation. The lines of longitude, on the other hand, are mapped one into the other. Now, let's put the whole thing together. And what we get in the upper right-hand part of the picture is a picture of the bilinear transformation which corresponds to this rotation of the sphere.